It's called partial fractions. Okay? For the partial fractions, the whole idea of this, before you start copying and give example, the whole idea of this is to decompose. To decompose a rational function inside the integral into its factors, or terms, rather, into its terms, so we can integrate easier. Okay? Let me give you an example. Imagine that we have this integral. Integral of, let's say, 5 over x squared plus 4x plus 3 dx. This one, just like that. Before I give you the definition and everything. Just by looking at that, can I apply substitution or by parts or the triangles or any of those to solve this one? Substitution, no, because the derivative of this one is not there. If you were to have a 2x plus 4, then maybe yeah. By parts, no, doesn't follow the pattern that we have seen. There's no exponential, no logarithmic, no trigonometric. Triangles, no, because this denominator doesn't follow the one of the three cases when you have x squared minus a squared, or a squared minus x squared, or x squared plus a squared. Okay? So for this one, when you have a rational function inside the integral, if the other ones don't work, and if the denominator can be factorized, then we can apply partial fractions. Okay? This is important also to consider that you have a rational function, but the q of x, which is the denominator, can be factorized. Not simplified, no, factorized. This can, sorry.
Eso es como una condición para...
Ajá.
Y si no, profe, si no está factorizada.
Well, there will be a lot of cases in where there is no way to factorize, but you have, for example, a term in a square. So I'll give you more examples with that. But mostly, the ones that we're going to see in this semester are the ones that you can factorize, and there's no way to apply the other procedures. Okay? So, one more condition is that the degree of the numerator has to be less than the degree of the denominator for this to start working. If it's the opposite case, where the degree of the denominator is less than the other one, we need to do something else. But we'll do that in an example there. Okay? Now, in this case, when you have a rational function, this can be factorized, and when you have factors of the denominator, if, for example, the denominator can be factorized in linear terms of the form ax plus b, then if that happens, we're going to separate the fraction in terms. So, terms in the integral. For every factor of the denominator, we're going to put a coefficient, a over ax plus b. For every factor. For every factor. For example, I have x plus b, the denominator will be in the integral a over x plus b, plus, if I have another linear factor, will be plus b over the other factor, and so on. Okay? Let me give you an example. Imagine this one. Can I factor this trinomial?
Yes.
Yeah. How? If you observe, in this case, I factorize the two into two binomials here. Both are linear factors. What do I mean by linear factors? That the degree for each one of the factors is degree 1. Now, if you want to separate, we're going to do this. For every factor that I have, I'm going to put a coefficient. A, B, C, whatever. So, in this case, I want to separate this into terms. 5 over x plus 1 times x plus 3 equal to separation A over x plus 1 plus B x plus 3. Okay? The whole idea of this is to separate this single fraction into components. So at the end, these small components can be integrated easier or faster. Okay? The only problem is that we don't have the and B. We don't have them. So something to get them. Once I get the a and b, now we can integrate. So what do? In this case, for example, I have this, I'll separate because of that case. Now what? We're going to multiply the whole equation, not just this part, the whole equation by the denominator. The denominator is all of this. X plus 1 times x plus 3, and on the other side the same thing. X plus 1, x plus 3. To do what? Well, in this case, if I multiply this times this, what happens to the denominator? Simplifies all of this over this, and I have just 5 equal to a over x plus 1, just this term, by the factor here, a x plus 3. This one cancels with this one, you get another one. Plus b times x plus 1. Okay? So far, okay? Now, in this case, we have two options to solve this. You can use system of equations, which could be a little complicated depending on the case. There's another way, which I think will be simpler for you. In this case, what we're going to do is we're going to try to transform this factor into a 0. And in another case, this one into 0 again, to get the values of the a and b. How? For example, first, if in this case, if x plus 3 is the one that you have, x has to be equal to what to make this 0? Minus 3. So now, if that happens, we have 5 equal to a times 0 plus b times minus 3 plus 1 minus 2. So 5 equal to minus 2b, b is equal to minus 5,000. You divide. That's for the b. Now, since I have another factor with x, we're also going to get that into 0. If x equal to what in this case? Minus 1. So again, 5 equal to a times minus 1 plus 3, 2 plus b times 0. So 5 equal to 2a, a is equal to, no, not 3, 5 halves. So now I have the values for a and b, and now I can change this integral and decompose it in its factors. A will be what? It's 5 halves over x plus 1 plus, well, minus 5 halves over x plus 3 dx. Now you have two single terms that can be integrated quickly, fast. Okay? 5 halves over x plus 1. Integral is going to be 5 halves is the coefficient. When you have, for example, 1 over x, what's the integral? ln of x. If you have 1 over x plus 1, what's the integral? Minus 5 halves ln of 3 plus c. That's the answer. Well, you can simplify a little more, but I'll accept that. If you want to simplify, you could simplify by knowing that this is 5 halves. It could be a common factor. Then you have ln of x plus 1 over x plus 3 plus c. That's the final solution. But this is bad. I just apply lots of logarithms. Subtraction of logarithms. Yeah.
Ahí donde está el...
Questions about the procedure?
No.
Yeah.
Cuando ya tienen los valores, ¿cómo se sacó lo que
Remember, if you have an integral of just 1 over x dx, the integral is what? ln of x. So you have x plus 1, there is no problem. ln of x plus 1. If it was, for example, 3x plus 1, you need to be careful with the 3. Because that is going to affect the final answer. But at the end, it's going to be another logarithm.
If it was x squared...
No, if it's x squared, then it's something different in the procedure. Okay? Questions? Okay, that's the case number one, when you divide into linear factors, different linear factors of Q of X. The second case is when you have linear factors but repeated. For example, when you have ax plus b as a factor but raised to a power. Let's say ax plus b to the square. Or, for example, you have x plus 1 to the square, or x plus 1 to the cube. Something like that. If that happens, it's almost the same as this, but for every single factor of this, you're going to apply a coefficient. So it will be a over ax plus b plus b over ax plus b to the square, so on, until you have the last one. What do I mean by this? I'm going to do the same thing, but it means that if you have raised to a power a linear factor, you're going to put terms for every single factor of this. Ax plus b to the square, all the way to n. If it was, for example, ax plus b to the cube, it would be a over x plus b over ax plus b to the square, plus c over ax plus b to the cube. Okay, we're going to do an example. Good. Can I erase? Okay, continue. ¿Cuántos casos hay, profe? 4. 2. Ya, un seco.
Hay más, pero no lo vamos a ver.
Ajá. Yeah, better. Okay. That one, for example, first, it's a rational function. Yeah. Can I fact the denominator?
No.
Yeah.
Yes.
2x minus 1 over, if I factorize this step by step, first common factor is x, so it becomes x squared plus 4x plus 4, and then a little more, 2x minus 1 over x times x plus 2 to the square. Yeah? In this case, what happens? I have three factors. One of them is linear, single x, but then you have x plus 2 to the square, repeated. So we're using actually both cases. What do I do? Would be 2x minus 1 over x plus 2 to the square equals, according to these two cases, the first one would be a over x for a single factor, plus, according to this, would be b over x plus 2 plus c over x plus 2 to the square. Why? Because those two correspond to this. One per each single factor of that one, the one that is repeating itself. Yeah? Then what? Same procedure. Multiply. So, this one becomes